Okay, so before we move forward with waves, I want to just differentiate between mechanical waves and electromagnetic waves. Mechanical waves can be broken down further into two categories. We have transverse waves and we have longitudinal waves. Both of those are subcategories of mechanical. So let's first just describe the difference between transverse and longitudinal. So a transverse wave is characterized by a wave that propagates perpendicularly to the direction of the disturbance. I'll explain. What I mean by this is maybe you've gone into a pool with some of your friends. So let's say you're in the pool and you're in a little tube. So let's just say this is someone in a pool. And this person is going to generate waves by oscillating up and down. So this person wants to create waves that are going to propagate outwardly. So even though the disturbance is happening along the y-plane, so let's just describe this as disturbance along the y-plane. The waves are going to propagate outward along the x-plane. Okay. So this would be a transverse wave. Another diagram could be, let's say I had like a little slinky and I created a pulse in that slinky. That disturbance happened in the vertical plane. However, the pulse is going to propagate in the horizontal plane. Okay, so that would be a transverse wave. Longitudinal waves, on the other hand, are characterized by a wave that propagates parallel to the disturbance. Parallel to the disturbance. In other words, for example, when you speak, you are creating pressure bands in the air molecules, high pressure, low pressure, high pressure, low pressure, high pressure, and so on. So the disturbance is happening along the x-plane. You're pushing air out. So disturbance happens on the x-plane. And the wave propagates on the x-plane. So the wave is traveling in the same direction as the disturbance is happening. So these particles are oscillating back and forth along the x-plane, and the wave is traveling on the x-plane. Whereas with transverse waves, the oscillation is happening along the y-plane, but the wave is traveling along the x-plane. Okay, so an example of longitudinal waves are sound waves. I want to just take a moment to talk about sound waves a little bit more. So let's say we have a tuning fork. I just want to label these regions of high pressure and low pressure. So let's say I have a tuning fork. And let's say we strike this tuning fork. So we are going to produce bands of high pressure, bands of low pressure. And these have names. Bands of high pressure and bands of low pressure. High pressure, low pressure, high pressure. Okay, so the reason that these bands are forming is because this is oscillating back and forth, and this is oscillating back and forth. So we get these regions of high pressure, which I'll point to over here. High pressure regions which are referred to as compressions. And these low pressure regions, which are known as rarefactions. Rarefactions. By the way, if we wanted to define one wavelength in a sound wave, we are going to go from one maximum to the next. So this would be 1 lambda. Okay. So now I want to go back to transverse waves, and I want to talk a little bit more about them. Transverse waves, again, are characterized by a disturbance that happens vertically, but results in horizontal movement. So this wave is going to travel to the right, and let's say I want to predict where an object experiencing this wave will be in the next moment. So let's say I have an object sitting right here in the context of this waveform, and this wave is traveling to the right. So what I'm going to do is I'm going to take the direction that this wave is moving in, and I'm going to draw a new waveform shifted slightly in that direction. Okay, so I'm going to recreate this exact same waveform next to the original diagram. And then this is going to allow me to see if that point is going to oscillate up or down. So now I've drawn my new waveform. Well, this point is going to be lifted up at the next moment in time because it would have to go up to fall on my new waveform. Okay, so the point A, so if an object were placed at point A, it would travel up in the next moment as this transverse wave passes through it. Okay, so let's do one more of those. So let's say, so this is again a transverse wave, so let's just separate longitudinal so we don't get confused. So let's say I have another wave, and let's say I have something like this, and let's say my point is, let's go right over here, we'll call this point B. And now let's have this transverse wave traveling to the left. Well, if it's traveling to the left, then I need to draw it shifted to the left. So I'm going to recreate this same wave just a moment later. And it should look exactly the same as the original, or as close as you can get it. Well, point B in the next moment would actually be traveling downward, because again it's a transverse wave, so it can only oscillate up and down. We're going to assume we have an object sitting here and this wave is passing through it. In the next moment it's going to be traveling down. So if an object were placed at point B, as this transverse wave passes through, it would travel downward.